Hi guys, my name is Jasmine, and today we're going to be taking a look at one of the more challenging LeetCode problems, and it's called Word Ladder 2. Now, this problem is an extension of the word ladder problem, and they're quite similar, but they're a little bit different, and we're going to be taking a look at it today. So without further ado, let's actually get started. Okay, so let's go over the problem description. Well, given two words, begin word and end word, and a dictionary called wordlist, return all the shortest transformation sequences from begin word to the end word, or an empty list if no such sequence exists. Each sequence should be returned as a list of words starting from begin word, and then some words after that, up until SK, which is noted here, SK is equal to the end word. So basically what it says is that we want to get from begin word to the end word. Now, here, let me just explain actually what transformation sequence is first. Well, a transformation sequence from one word to the another word, or in this example, end word, using a dictionary that is given to us as the input, here is wordless, is a sequence of words that starts from begin word, ends with the end word. However, here we have a set of words that have to be in the word list. Now, the important thing here to consider is that each word in this sequence uh, only differs by one from one single letter from its adjacent words. For example, S1 only differs by one letter from begin word, and the same goes for S2. S2 only differs by one letter from S1, and so on and so on. So basically, what we need to do here is we want to get to from begin word to transform begin word to end word. Now, along the way, we have to use all these words from the word list to that to help us do that. Now, here's the thing: we need to place them in an order that um, each word only differs by one letter from its adjacent words. So I guess you'll understand better if with an example. Now, one thing to note that is that this question only needs the shortest transformation sequence. So there might be other ways to go about this problem, but what we need here is the shortest path. So let's actually start with this problem. Okay, so here we have begin word, hit, and end word, cog, and this is a word list, a list of words that we have here. Now, one simple way to solve this problem is we can use a graph to represent all the words and find the shortest path, like this. So the hit word is our starting node here, and cog is our last word here. Now, along the way, we have to place these nodes in a way that each node only differs by one letter from its adjacent nodes. Like, for example, hit only differs by one letter I and O here with hot. And hot has dot and lot that only differ by one letter. Here, for example, is D and L that are different uh, from H, but all the other letters are the same. So this is how we're going to go about it. Now, how do we find the shortest path? Well, here's the thing. We can actually, let's actually traverse all the paths and see which one is actually the shortest. So, the first path that we can take is we can go from hit to hot. Well, they only differ by one letter. And then we can go to dot. They also only differ by one letter. And then we can go to doc, one are also differ by one letter. And here we can go to cock. I hope you can see that each word only differs by one, uh, sorry, by one letter. Now, this is path 1, okay? Now let's actually find path 2. So another way to go about it is we can, start from here. Here are the same as the previous path. However, instead of choosing dot, we can actually go to lot and then go to lock and then go to cock here. So this is our second path. Now, what's the length of this path? Well, the length of this path is 5, 5, and this is also 5. So they have the same length. Now, if you recall, and the question says we have to return all the shortest path. So meaning that there could be more than one shortest path. So another thing is, well, there's other ways to go about it too, actually. Let's say we want to go from hit to hot, and then go to dot, and then we want to go to lot. And then from then we can, do the same thing as path 2. So as you can see, this isn't the shortest path. The length of this path is actually 6. So it's not the shortest path. If we want to go from after hot, we want to go from dot to lot. Even though they only differ by one letter, this doesn't give us the shortest path. You could try the same, another path from hot and then to lot, and then we can go from lot to dot, and then the same as path 1. The rest is the same as path 1. Now, it's possible, but it also gives us the length of 6. So it's not desirable when we have the short another other routes that give us a length of 5. So we choose these two paths. So basically, we want to go from hit to hot, and then hot to dot, and then from dot to dock and cock. So another another path. This is like our path 1. This is path 2. They both have the same length. We can go from hit to hot, same as the above. However, we have the option, instead of going to dot, we can go to lot. And then after that, we can go to lock. And finally, we arrive at cock. So we should return a list that contains all these words as our shortest transformation sequence. Like basically, we return 2 lists that contains this sequence and this sequence. Now, one way to go about it, if you recall, in these sort of questions, when we want to find the shortest path in a graph, is to use BFS. Now, how to implement it, I'm gonna actually go into details in the next section, but just for now, keep that in mind, that if we want to go from one node to another node, and we want to find the shortest path, that's basically what BFS does. So now, before we actually move on to the next part, let's review some of the constraints of this question. So it says that begin word, all the words' length are between 1 and 5. Like no word has more than 5 length. The length of each word is 5 maximum. Now, the length of every word is the same, like end word and begin word have the same length. However, as you can see here, every word in the word list length is the same as the begin word. So basically what it says is that all these words here have the same length. Like for example, hot, dot, dog, and lot, and cog have basically all 3 letters in them, and also the begin word has 3 letters. So they should all be 3. The length of all of these words are 3. Now, all of them are in lowercase English. Um, all the words are unique in the word list, and begin word and end word are not the same. So they're unique. They are different. They're different. Now, one other thing to mention here is that no two in the word list that we're given here, we should have all the words that we're going to use in these paths, including the end word. But it's fine if we don't have the begin word included in our word list, you know. But all the other words that we're going to use in this path must be in the word list. Okay, now let's actually move on to the algorithm part. All right, so let's actually move on to the algorithm section. Like I've mentioned, there are a couple ways to go about it. You can use DFS or a combination of BFS and backtracking, which is the solution we're going to be overviewing in this algorithm section. So, first things first, if you remember uh, anything from BFS, BFS is a graph traversal method which aims to find the shortest path possible by traversing level-wise from the source node. Meaning that we're going to go over the source node, and then after that, we're going to examine each level, each node in every level, and then move on to the next level, and after that to the next level. That's why we have level here. And the data structure we're going to be using in this algorithm is Q. That's the data structure we use in BFS. So we're gonna, in each level, we're gonna push the current words into the queue, sorry. And then after we're done traversing that level, we're gonna pop them out of the queue and move on to the next level. Now we have a current word, and then we have a new word, which is the possible combinations that are extracted by changing each letter uh, each letter of the word, and if it matches any pattern that also exists in the words list, we're going to actually store it in the hash map. And after we've done traversing the current level, we're going to move on to the next level and increase the level by 1. So the first thing, we're going to start with begin word. Now we're gonna push it into the queue, and it's gonna be our current word, and we're gonna actually see all the possible combinations. So how do we see all the possible combinations? Well, here we change each letter from A to Z. First, we start with the first character in the word and change it from A to Z and see if it matches any pattern in the words list. Now, you have to also note that here we don't we ignore hit because it's the same as the current word. So we ignore it. But once we do it with the second character in the current word, we find out that there is a combination hot that also exists in the words list. So what we do is we pop hit out of the queue and push hit into the queue. And we're going to actually store it in a hash map like this. And we also have to, after we found this pattern, we also have to go over to the next character or last character, T, and do the same thing, change it from A to Z, and see if we find any matching pattern. So what we realized we haven't found any matching pattern. So we're done here. So we're gonna actually mark hot as visited. So we've already visited it. And after we move on to the next level, we're going to actually delete it from the words list because we've visited this node and we don't want to visit it again. So that's why we deleted from the words list. So here, because the first level only contains the source node or our begin word, we're going to move on to the next level, and we're going to eliminate hit. So here we move on to the next element, which is hot, current element. And we're going to repeat the same algorithm here. and change the first letter of the word from A to Z. Now, first we encounter dot. So dot is a pattern, is a matching pattern that also exists in the words list. Now we mark it as visited, and we're going to store it in the hash map. And what we're going to do is we're going to push it to the queue and pop hot out of the queue. And we do the same thing. We do the same thing until we get to lot. So here we also have another matching pattern. And so we mark it as visited and push it to the queue and also store it in the hash map. We're still on level 1, by the way. So after that, we do the same thing with the third letter, but we don't find any matching pattern. So we move on to the next word. So here, the next word exists in the next level. We increase the level by 1. So once we actually moved on to the next level, we're going to eliminate the previously visited nodes that we've marked, like here, dot and lot. We're going to actually eliminate them in the new words list. So we'll go over dot. So here we have dot, and we're going to repeat the same algorithm here as well. We don't find any matching pattern by changing the first letter. By changing the second letter, we don't find any matching pattern either. But if we change the third letter to G, we're going to find doc, which also exists in the words list. So mark it as visited and push dot out of the queue. Pop dot out of the queue and push dog in. We also have to store it here like this. And we're going to mark it as visited. And here we have dog. So we're still on level 2, by the way, because we have lot to examine. So our current word is going to be lot. We do the same thing here until we find log. So it's a matching pattern. So we're going to actually mark it as visited. We're still in the same level, like I mentioned. And we're going to store it here. Lot, log, it's a matching pattern. And we're going to pop it out of the queue and push log in. Once we've done this, log and log, we're going to actually move on to the next level, which is the third level, and we're going to actually eliminate log and lot. Sorry, log and doc. So here we only have cog in the third level. So the current word is going to be doc, and we're going to go over all the possible combination for the first letter in the word dog. We get cog out of it, which also exists in the words list. Now here, we're going to store it here and push it to the queue. But we're going to mark it as visited. However, in this, because we're in the same level, there is another word, log, which also can transform into cog. So that's why we don't eliminate it once we're still traversing the same level. After we've done traversing the level, we're going to delete it. So we're also going to store log. We're going to store a log to cog here, like this. And we're still on the third level. And we're going to pop log out and push cog in. So, and also eliminate cog from the words list altogether. Now, here we can change our current word to cog, but since cog is our end word equals our end word, we're going to stop here because we've traversed the whole all the possible combinations and we got to the end point, which is what the question asked us. Now, after that, we're going to use backtracking to store all these like patterns into a list. So now that we went over the BFS part, we have to find the length of the path we just traversed. So the length of the path is level plus 1. which our current level is 4, plus 1 is going to be 5. As we previously discussed in the problem explanation section, the shortest path length is also 5. So why do we use backtracking? So here is the important part. We need to find these paths and all the possible paths and return them in a list. So we need to store all these paths in a list and then return them as the question demands as the output. So what we're going to do here is we're going to go over, now that we have the map, we're going to go over all the possible transformations starting from the begin word, which is hit. And then we'll see we ask this part, what is the next possible transformation? Well, the next possible transformation is hot according to the map that we've created. So it's going to be hot here. And we need a list to store the current path into it. So this is going to be a list. We're going to store, for now, we're going to have hit and hot. So after that, what is the next possible transformation after hot? Well, there are actually two transformations. There is dot and lot. So you can choose whichever you want. We have to like choose one of these at first and then we'll backtrack and choose the other one. But for now, I want to go with dot. So after dot, we actually add it to the current path. Uh, and then after that, what is the next possible transformation? Obviously, it's dog. So we're going to add dog to the list as well. And then what's the next possible transformation? Well, it's cock, which is the end word. So now that we've reached the end word, we're going to store this list, this first path, into the set of paths here, which is a list that contains all the possible shortest paths. So we add it to here, and then here we're going to backtrack. This is the backtracking step. So we're going to go from cog to dog, and then we're going to examine it again. So what's like the uh, possible transformation from dog to cog? Well, there is no other transformation. So we're going to remove cog from the list of the current paths, and we're going to backtrack again. We're going to go to the previous dot, and then we examine it again. What is the another transformation we can have, perhaps? Well, according to the map, there's no other transformation. It's only dot. So we backtrack again. And then here we have another trend, and we remove it from the list, by the way, current path. We remove it from the current path. So now we have hit and hot. And now we're at hot. And what is the next possible transformation? Well, another transformation we can have is lot. So we add it to the current path and here. And then after lot is dog. Sorry, it's log. And we add it to the path. And after that, there is cock, which is the end word, and we stop here. So this is the second path, which is the same length as the first path. It's also 5. And we first add this one to the set of paths, like here. Okay, so after that, we backtrack again from where we are and examine if we have any other path, if there's any other path that is left and we haven't like discovered it yet. So we backtrack again. We go from cock to log and remove cock from the current path. So like this, we remove it from the. So there's no other transformation from log to cock. There's just one. And then we backtrack again then. Then after that we backtrack again, and then There's no other transformation other than these two. So we backtrack again and we remove it from the list. So we reach to the begin word, and obviously there's no other transformation other than hot, so we remove it from the current path. Now the current path is empty, and we only have two possible paths here stored, and this is the final answer that we need to return.
Okay, so let's actually examine the code, Java code for this problem. So we have a couple data structures for this problem, and the first one, as explained earlier, is a hash map called a JSON list. It contains each word and its neighboring words that are only different by one letter. And this is our current path. It's a list that contains the current path that we're in. And the third data structure is the shortest paths. This contains all the shortest paths possible, and it's a list of lists because we can have more than one shortest paths. Now, this find ladders is our main function, and it takes three parameters called begin word, end word, and a list of words called word list. And since for the BFS section, we need an unordered data structure, an unordered list, so we can efficiently remove the words when we don't need them anymore. We remove each layer. We instead of using a list, we use a set. So we copy all the words from the word list here, and then to create our graph, we actually call the BFS, and I'll explain all these functions in a minute. Since every path starts with begin word, obviously we first add the begin word to our current path, and then we backtrack. This is the backtracking step. And if we can find here, we can find in our current path, we can find a path between begin word and the end word. We're going to store it in our shortest paths and return it as our answer. Now let's actually examine the BFS function here. This is pretty much just like a regular BFS, and it takes three parameters, a set, and two strings, begin word and end word. As explained earlier, we use a queue data structure for our BFS, and obviously the first word to add is the begin word, and after we add it to the queue, we can remove it because it's our first layer, and as explained earlier, we remove each layer after we're done examining it. And here, if the word list contains begin word, we're going to remove it from we're going to remove begin word, which is our first layer, and it only contains one word from our word list. So here, while our queue isn't empty, what we basically want to do is we're going to find all the neighbors of each word and save it in our adjacent list. Now here we have a visited list, which contains all the words of the current layer that we're visiting. So we loop over, in order to do that, we loop over our queue and start with the most front element, and we save it in the current word because we don't need it anymore. We have to pop it out of the queue, and here we find all the neighbors of that current word using the find neighbors function, and I'll explain this one in a bit. So after we find all the neighbors, what we need to do, we have to add this to our adjacent list. We have to add the current word and all of its neighbors to that list. So we loop over all the words in that neighbors list. Obviously, we add each of them to the visited list, and then if we don't have the current word in our adjacent list, we add it with an empty list. And then we can add the words to that empty list. Now, if that's not the case, if it already exists in our adjacent list, we only add the particular word that we're looping over to the list of its adjacent nodes, the current word's adjacent nodes. And after we're done doing that, as previously explained, we have to remove the words of the current layer. And in order to do that, we loop over the visited list, and we remove each word from our word list. Now, what is the function find neighbors? So here's the find neighbors function. It's a very simple one. It takes a word and finds all of its neighbors. It takes a word and a word list because we want to see whether it exists in that word list or not. And this is our neighbors list. Here we store all the characters of our word in a char array called char list. And what we basically do here, we change each letter in that word to see whether it creates a new word that exists in our word list. So we save it the original character in our old char, and then we loop over each letter in that word, and we change it from A to Z, see whether it creates a new word. If C equals our old character, meaning that it's the same word, or we create a new word that does not exist in our word list, we skip it, we don't need it. If that's not the case, then we add it to our neighbors list and then change the ith character back to its original form, and ultimately return the neighbors. So our final function is backtrack. Here we take two inputs, source and destination. Basically, we want to see whether there's a path between the two. If there is, we're going to store it in our shortest paths. So like I said, if source equals destination, meaning that we've reached the destination, we're going to store our current path that we're on in a list and then add it to our shortest paths because there's a way. However, if that's not the case, if that's not the case, we haven't reached our destination, what we do is that first off, we're going to loop over all the neighbors of our source, whether we can to see whether we can find a path between the neighbors and our destination. So we add that we add the ith neighbor to our current path, and then we recursively call backtrack with that ith word to see whether there is a path between that and destination. So we continue this until we reach the destination. Now there is a third possibility, and that is if our adjacent list does not contain our source. If it doesn't, we skip it. We don't need it. We can't do anything with it. Now let's actually put this code in LeetCode and see what are the results. Let's submit our code here. Hit the submit button. So it was successfully accepted. Now let's talk about complexity. Well, the time complexity of this code is nk squared plus alpha. Now n is the number of words in the word list, and k is the maximum length of a word. And the reason for that is we have the find neighbors function, and the complexity of this part is k squared, and because we want to find the neighbors of n words, it's going to have the complexity of nk squared ultimately. And in the backtracking step, we're going to find all the possible paths, so it's going to be a constant like alpha. And as for time, for space complexity, because we copy all of our words in the word list, n words with k length in a set, we're going to have nk, O of nk, as our space complexity. Now, I hope you enjoyed this tutorial, and I'll see you in the next ones.